in Chapter 4, we will be looking at alkanes. We'll just get started by talking about what an alkane is. Now, we've already seen the definition of an alkane, but just to reiterate what it is, an alkane is an alkanes are aliphatic hydrocarbons having only carbon-carbon and carbon-hydrogen sigma bonds. There are no pi bonds. So this means it does not include alkenes and it does not include alkynes. And it definitely doesn't include aromatic because aromatic are not part of the aliphatic. We'll find that in alkanes, all of our carbons are sp3 hybridized, meaning they have the tetrahedral geometry and they have the 109.5 degree bond angle. There are two categories of alkanes, and our two categories of alkanes are going to be acyclic alkanes with the formula CN2N plus or H2N plus 1, and they contain only linear and branched alkanes. These are also called saturated hydrocarbons. So saturated. Saturated means it has as much hydrogen as it can have. So acyclic alkanes, this is just an example. Undecane has 11 carbons, 24 hydrogens, and you'll see it fits in that formula. Cyclic alkanes they're just like these acyclic ones, except they contain one or more rings. And you'll see that they have two fewer hydrogens, and we'll talk about that a little bit later. But cycloalkanes, here's one of them, which is cyclohexane. Later in this chapter, we're going to be talking about cyclohexane quite a bit. When it comes to acyclic alkanes, let's just start with the smallest ones, methane, ethane, and propane. Methane is CH4. It is the simplest alkane. Here is our Lewis structure for it. So 4 carbons, of course, it is with 4 domains. It is a tetrahedral geometry, sp3 hybridized, as we mentioned. And so this is our 3-dimensional representation of it. And here is a ball and stick. If you were to make it with molecular models, that's what it would look like. Ethane, here is ethane. It's C2H6. And again, it's not a flat molecule like this. It's 3-dimensional. We've got 2 sp3 hybridized carbons, and you will see here, this is what our ball and stick model would look like. Propane has 3 carbons, and so propane with 3 carbons. Here is our skeletal type structure for it, and then here is a 3D representation and a ball and stick model. All right, so that is methane, ethane, and propane. Before we go to butane, we do want to go to butane. When we get to butane, we have constitutional isomers. It's possible to have more than one version of butane. So constitutional isomers, just as a reminder, are molecules with the same molecular formula that differ in the ways the atoms are connected to each other. So butane and isobutane both have the formula C4H10, but they are constitutional isomers of each other. So butane, 4 carbons in a row. Isobutane has 3 carbons in a row with a single methyl group attached to the middle carbon. Now, a little bit later when we get to naming, later in this video, when we get to naming, we will talk about how we name substituents and things like that. Now, one thing that I want to point out is that just because you can draw something different doesn't necessarily make it a constitutional isomer. For butane, all of these are equivalent structures. They have exactly the same connectivity, so they are not constitutional isomers of each other. They're just different drawings. So here for butane, you'll see we've got 4 carbons in the long chain here, and then 10 hydrogens attached to it. Well, if you make a little kink in it, it's still butane. And in fact, we need to remember with Lewis structures do not imply stereochemistry. So Lewis structures like this do not imply stereochemistry. So we can't really get anything out of this. In addition to that, here is another one. So again, 4 carbons in a row, all of the same atoms are connected to each other. We can draw it in various different ways. When it comes to the skeletal structures, here this is butane. This is also butane. This is also butane. That is also butane. So all of these are the same thing. They have the same meaning, and you can't think of them as different molecules. All right, so now we're on to pentane. Pentane is 5 carbons, all right? So it's a 5 carbon alkane, and it can be drawn in a variety of ways. Again, these are not constitutional isomers. So we've got pentane, this is pentane, that's pentane, that's pentane. They are just drawn slightly differently, and they mean the same thing. All right. Pentane does have 2 constitutional isomers, isopentane and neopentane, but again, this is different connectivity. So here we've got a 4-carbon chain with a methyl group on the second carbon, and then here we've got a 3-carbon chain with 2 methyl groups on the second carbon. So those are different molecules. All right, so our summary for the straight chain alkanes, we went up through pentane. If we have 6 carbons, it's hexane, 7 is heptane, 8 is octane. So those prefixes make sense. Nonane for 9, decane for 10, undecane for 11, dodecane for 12, tridecane, tetradecane, and pentadecane for 13, 14, and 15. And then here we've got 20 carbons, and that is icosane. So icosane, not to be confused with iocane, which is colorless, odorless poison from Australia. If we look here, the number of constitutional isomers, we'll see as we increase the number of carbons, the number of constitutional isomers increases pretty dramatically. And so that means that I'm not going to ask you on a test to give me all of the isomers of decane. That would be cruel. All right, so let's look at number 3 on the in-class assignment. Okay, so here it says draw the 5 constitutional isomers having the molecular formula C6H14. Now, you could do this with Lewis structures, but I find that it is a lot easier to do this with skeletal structures. So for 6 carbons, we'll do 1, 2, 3, 4, 5, 6. And so that is our first one, 6 carbons. Now, there's no other way to draw that. If we draw it like where we bend it in a different way, that's still going to be hexane. So now we need to go to 5 carbons and see how many different ways we can put substituents on there. So with 5 carbons, we'll find that there are 2 different locations that we could put the 6th carbon. And that is, we could put it at the 2 position right here, or we could put it at the 3 position there. And so we will find that those are our 2 possibilities. If we put it on the 4th carbon instead, that will be identical to putting it on the 2nd carbon, so that would not be a different isomer. All right, now we want to look at when we have 4. 1, 2, 3, 4. All right, so our possibilities here are we could put 2 methyl groups onto the 2nd carbon, and that would be one of our possibilities. And then our final possibility is if we put a methyl group onto the 2nd carbon and a methyl group onto the 3rd carbon. With a methyl on the 2nd and 3rd, that would be our final isomer. Now, sometimes people ask, well, what if I put an ethyl group? What if I put a 4-carbon chain and put an ethyl group on that 2nd carbon? And let me show you what that would look like. Okay. Well, the problem with this is a 5-carbon chain, 1, 2, 3, 4, 5, and we've got a methyl on the 3rd carbon. So that one is identical to this structure. All right. So we want to go back here to our presentation, and we want to look at cycloalkanes. So with cycloalkanes, we will find that they are very similar to the straight chain alkanes, but they just happen to have a ring in them. All right. They do have fewer hydrogens, specifically 2 fewer hydrogens for every ring. And that's 2 fewer hydrogens than the corresponding alkane would. Simple cycloalkanes are named by adding a prefix cyclo in front of the corresponding acyclic alkane name. And so here are a few examples. We've got cyclopropane, cyclobutane, cyclopentane, and cyclohexane. Let's look at number 9. So we want to draw the 5 constitutional isomers that have a molecular formula of C5H10. All right, so that is, and have at least one ring. We have to have the one ring, otherwise we're going to have all kinds of double bonds and stuff that we can put in. So here we've got cyclopentane. All right, and since there's no other way to draw that, we're going to go to the situation where we have 4 carbons in the ring, and there we would have a methyl substituent, so that would be that one. And then we can go down to 3 carbons, and with 3 carbons, we need to have 2 more carbons on there, so one possibility would be to add an ethyl group. Another possibility would be to add 2 methyl groups to the same carbon, and then our final possibility would be to add a methyl group to one carbon and a methyl group to another carbon. All right, so there you go. That would be the 5 constitutional isomers that have that formula. Okay, so now we want to talk about nomenclature. All right, so all chemicals can be named using a systematic method. It was first introduced by the International Union of Pure and Applied Chemistry. The IUPAC is what we say for short. And that first official system was in 1892, and they have updated it over the years to add chemistries they had no idea they were going to need to name. We'll find that the same chemicals that you get from the IUPAC name often have common names, and that those common names are widely used. Sometimes the IUPAC makes changes to the rules to help avoid confusion, but in doing so, you'll find that previous IUPAC names often stick around for decades, and that sometimes your chemistry professor might still use an old version of the name. And just as an example of a compound that has several different names, this is a compound. It's got a double bond between the first and the second carbon. And so some of the common names that it has, 1-butylene. We've got alpha-butylene. I've even seen the name, although I haven't heard anybody ever say this, like I haven't ever talked to anybody who says this, ethylene. So it's got an ethyl group attached to an ethylene. The IUPAC name up until 1993, it was just called 1-butene, and so that is the way that I learned this. I will often look at that and I'll say 1-butene. However, if you look at the 1993 recommendation, you will see but-1-ene as the official name. Since I learned it as 1-butene, you might hear me say the word 1-butene instead of but-1-ene. You'll just have to accommodate me. That one's not too terribly different. So, all right, so let's look at naming some alkanes. Every organic chemical is going to have three parts. The first part is going to be the parent name, and it has the number of carbons in the longest continuous chain. We're also going to have the suffix, and so that of course goes at the end, and the suffix tells us what what functional group is present. For this particular chapter, ane is our functional group because it's alkanes. The prefix is going to reveal the identity, location, and number of substituents attached to the carbon chain. Sometimes this is not necessary if there are no substituents. So this would be the order. Of course, the prefix goes in the front, the suffix goes at the end, and the parent is going to go in the middle. So usually coming up with the parent and the suffix is going to be your easiest first approach, and then figuring out your prefixes afterwards. So when we are naming substituents that are made from alkanes, we can take any alkane and we can call it an alkyl group, provided that we make it into a substituent. In order to make it a substituent, we need to remove one hydrogen atom from the alkane. All right. To name the alkyl group, we're going to change the ane of the parent to eel. So just as a few examples, methane, we remove one hydrogen and we get CH3, it will become methyl. Ethane becomes ethyl. Propane becomes propyl. And butane becomes butyl. So those are all pretty obvious what those are. When we have three carbon chains, propyl, well, it turns out there's more than one way to have a propyl substituent. So if we've got the three carbon chain or the four carbon chain, we'll do the four carbon chain on the next page. It's a bit more complicated because there's more than one type of hydrogen. As an example, propane has both primary and secondary hydrogens. So if you look at the structure for propane, there's three carbons. Well, there's the carbons on the end, which are primary carbons. They have primary hydrogens. And then there's the carbons in the middle. The secondary carbons have secondary hydrogens. If you remove a primary hydrogen to make your alkyl group, we're going to call that a propyl group. If you remove the secondary hydrogen from propane, we will call it an isopropyl group. So you will need to memorize these because these are common enough that we need to have them as part of our IUPAC nomenclature. So propyl and isopropyl, that's pretty easy. For the four carbon chains, it's a little bit more difficult, but it's not too bad. There are two different butane isomers, butane and isobutane, and each of those has two different types of hydrogens. So with two different types on two different molecules, that means we can get four different possible substituents. And so here we've got butane, the four carbon chain, so 1, 2, 3, 4. If we remove the primary hydrogen, we're going to get just the regular butyl. So 1, 2, 3, 4. Straight chain alkyl group. If we remove the secondary hydrogen, we're going to call it sec-butyl, and the sec just means secondary. So we had a secondary carbon, we removed it, and now we're attaching it to the parent. If we have 2-methylpropane or isobutane, there are two different types of hydrogens. So there's four carbons, 1, 2, 3, 4 carbons. And then there's a tertiary hydrogen here and a primary hydrogen on, there's actually 9 of those primary hydrogens. We're just removing one of them. So if we remove one of those, we will get an isobutyl substituent. And if we remove the tertiary hydrogen, we will get what's called a tert-butyl substituent. So we'll get a tert-butyl. All right, so now we want to get to the naming part. How do we go about naming it? Well, the very first step is to find the parent chain or the longest continuous carbon chain and then add the suffix. So when we look at a structure like this, we want to count all the possibilities. You don't need to count all of the possibilities. You just need to make sure that there's not one chain that's like sneaking in there. So if we look, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons that direction. 1, 2, 3, 4, 5, 6, 7 that way. So since we have 2 possibilities there, the 8, since that 8 carbons, that's more, we're going to say that is the correct way to do it. So we'll use the prefix, or the parent oct, and the suffix ane, because it's an alkane. So this is an alkane parent. Now, one thing you want to be careful about is that it doesn't matter if the chain bends or if it is straight. So this is how we had it drawn, but it could be drawn like this, and this is perfectly legitimate way to draw that parent chain, as is this. Now, it's a bit confusing, and it would be kind of weird to do so, but sometimes when people draw structures, you need to just be aware that that the way they drew it doesn't always make sense to you. So count the longest chain. All right, naming structures with chains of equal length. So it is sometimes possible that you will get 2 chains of equal length within your compound. You want to pick the chain that has more substituents. All right, in this example, all right, in the following example, 2 chains have the same carbon, same alkane, have 7 carbons in their chain. So if we look here, so 1, 2, 3, 4, 5, 6, 7, but you could count it from this way, 1, 2, 3, 4, 5, 6, 7. Well, you would think, oh, well, maybe they're both equally good. No. We want to pick the one that has more substituents. So one chain gives you 2 substituents, and the other way gives you 1 substituent. So we're going to pick the one that has 2 substituents. So that's just something to keep in mind when you're naming something. All right, now for numbering the alkanes with the substituents. And the numbering is important for determining where the substituents go. You want to number the atoms in the carbon chain to give the first substituent the lowest possible number. So going back to the structure that we saw a little bit earlier, so here is our 8 carbon chain. If we number it from the left side, our first substituent is going to be at carbon number 2. If we number it from the right side, our first substituent is at carbon 3. Well, we want to give the lowest possible number to the first substituent. And so this is the correct way to do it. So this is going to be carbon number 2. And then these will be 5 and 6 over here. All right, so number it to give the first substituent the lowest possible number. Well, what if both directions give the same number? So if that's the case, then look for the next substituent. All right, and so in this case, if we number from the left, you'll see 1, 2. The first substituent is at position 2. If we number from the right, the first substituent is at position 2. So now we need to look for the next substituent. So 1, 2, 3. Our next substituent is at carbon 3. Here, our next substituent, 1, 2, 3, 4, is at carbon 4. So we want to keep doing this until we get to a point of differentiation. We could have a parent chain that's got 100 carbons in it, and then there's substituents all along the way, and we want to keep counting until we find one point of differentiation. So, and then that one point, it's going to go to the smaller number. So this will be the correct way to number this particular molecule. All right, well, what if there's not another substituent? All right, when numbering a carbon chain and it gives you the same numbers from either end of the chain, then assign the lower number alphabetically to the first substituent. If there's no difference in the substituent, then it doesn't matter which way you number it. But in this case here, you'll see that if we count from this side, our first substituent is at carbon 3, and it is an ethyl. And our second substituent is at carbon 5, and it's a methyl. If we count from the right side, 1, 2, 3, our first substituent is the methyl at carbon 3 and ethyl at carbon 5. Well, here is where we apply our alphabetical rule. This, of course, means you need to know your alphabet. But I have a feeling that you know your alphabet already. All right, so there we go. So now we've got that rule taken care of. When it comes to naming the substituents, we want to name and number the substituents. So once we've got the correct numbering, and we're going back to that molecule that we were looking at a little bit earlier, we numbered from the left side. We decided there were 8 carbons in the chain. Well, at carbon 2, we have a methyl. At carbon 6, we have a methyl. And at carbon 5, we have an ethyl. All right, we're going to name them all as alkyl groups, so methyl and ethyl are correct. Every carbon belongs either to the longest chain or to a substituent, but it can't belong to both. And we also need to make sure that every carbon is accounted for. If you leave a carbon out, then something is wrong. Each substituent needs its own number, even if it's on the same substituent, and we'll see that a little bit later. So even if it's on the same substituent, it still needs its own number. All right, if 2 or more identical substituents, like the methyl here, right? We have a methyl at 2 and at 6. If 2 or more identical substituents are bonded to the longest chain, you use prefixes to indicate how many. So if there's 2, it would be di. So in this case, we would have a 2,6-dimethyl. 3 is tri, 4 is tetra, penta for 5, hexa for 6, and so on and so forth. All right, and now we want to complete our structure names. So combine everything together: parent, your substituents, your parents, and your suffix. So here our parent is oct. Our suffix is ane, so octane is our longest chain. We've got a 2,6-dimethyl and a 5-ethyl, and we want to precede the parent, the name of the parent, by the names of the substituents. So the substituents are going to go out front. When we have more than one grouping of substituents, here we've got dimethyl and ethyl, we want to list it so that the names of the substituents are alphabetized. And we want to ignore prefixes like, di, tri, and tetra, and all the other ones, including tert and sec. We want to ignore those, but we don't ignore iso. So like isopropyl and isobutyl, those are going to be alphabetically at position I rather than P or B. Whoever came up with that rule, I don't know, but that's just how it works. Somebody sat in a long meeting at IUPAC, and they probably argued about it, and they said, well, this is how everybody's doing it, so this is how we're going to do it. All right, we want to precede the name of each substituent by a number that indicates its location, and that's why we have the 2,6. We want to separate commas, separate numbers by commas, and separate numbers from letters by hyphens. All right, so the name of the alkane is a single word with no spaces after the hyphen, and we'll find that our last substituent is not going to have a space in between that substituent and our parent. So we're just going to cram it all together. So this becomes the name of this particular structure: 5-ethyl 2,6-dimethyl octane. The ethyl comes before methyl, and because E comes before M in the alphabet. All right, so we now want to look at number 40 and 43. So here is number 43 or number 40, and I like this particular one because it's kind of challenging and it's kind of fun. All right, so we've got 3-ethyl 2-methyl hexane. If I ask you to draw a structure given the IUPAC name, then the way I recommend it is to draw the parent first. 1, 2, 3, 4, 5, 6. So there's 6 carbons in that chain, and then put your substituents in. And unless you need to, just number from the left, unless you have some other reason to number from the right. So we're going to number it from the left, and at our 3 position, we've got an ethyl. All right. Doesn't matter if you zig to the left or zag to the right. That's okay. All right. So 1, 2, 3, 4, 5, 6. So that's on our 3rd position. And at position 2, we've got a methyl. If you get a really, really long chain, sometimes it's worthwhile to number it. And when we do dodecane here in a minute, I will number it because of that very reason. But anyway, that is our structure for 3-ethyl, 2-methyl hexane. All right, 4-isopropyl, 2,4,5-trimethyl heptane. Well, heptane is 7. So 1, 2, 3, 4, 5, 6, 7. And at the 4 position, so 1, 2, 3, 4. At the 4 position, we're going to have an isopropyl and a methyl. So I'm going to do an isopropyl and a methyl. All right, and then at the 1, 2 position, we're also going to have another methyl. So 2, 4, and then here at the 5 position, we will have a methyl. So 4 isopropyl, 2,4,5 trimethyl, 1. So 2,4,5, and heptane, 1, 2, 3, 4, 5, 6, 7. Okay, so 6 isopropyl, 2,3-dimethyl dodecane. Well, dodecane is 12. So we're going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here, this one is so long that I'm going to go ahead and number it. So I'm going to call 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, and one thing that I want to point out, you'll notice that I put the number kind of in the crook, right, in the part that's the inside the point. And that's because you should always put your substituents on the pointy side. So you notice how I put the substituent there and there, there and there. I didn't put it on this side. Technically, you can draw it where it's on this side, but it's confusing and not very appealing. So, all right. So 6 at the 6th position, we've got an isopropyl. So there's an isopropyl, and at the 2 and 3 position, we've got a methyl. So 1, 2, and 3. So 6 isopropyl, 2,3-dimethyl dodecane, and that is our structure there. All right, 2,2,6,6,7 pentamethyl octane. All right, octane is our parent. So 1, 2, 3, 4, 5, 6, 7, 8. And numbering, I'm just going to number from the left. So 1, 2. At the 2 position, we've got 2 methyls. So 1, 2. So there's 2 methyls. And then 3, 4, 5, 6. At the 6th position, we've got 2 methyls as well. And then at the 7 position, we've got a methyl. So again, that would be 2,2,6,6,7 pentamethyl octane. And that would be our correct structure there. So let's look at number 43 on our in-class assignment. And this one is kind of fun. And so the way I use the word fun is a little weird because, well, you know, I'm a chemist. So each of the following IUPAC names is incorrect. Explain why and give the correct IUPAC name. The best way to do this is to draw it and then figure out what's wrong with the name. So heptane here is our parent chain, according to this. I'm not going to put numbering on it because we may need to number afterwards. 1, 2, 3, 4, 5, 6, 7. At the 2 position, we've got 2 methyls. So 1, 2, 3, 4. At the 4 position, we have an ethyl. All right, well, let's check our longest chain. So 7 is our longest chain. There's no other way to do this. 1, 2, 3, 4, 5, 6. That won't work. So 7 is our longest chain, so that's right. Numbering it from the left side is correct because if we number from the right side, our first substituent would be 4. So 1, 2, 3, 4, 5, 6, 7. So there's nothing wrong with the numbering. Now we need to look at the substituents. We've got the correct numbers. What we don't have correct is that ethyl comes before methyl alphabetically. And so this one is pretty easy to fix. The proper name for this is going to be 4-ethyl 2,2 dimethyl heptane. And that is our correct name. All right, 5-ethyl 2-methyl hexane. So 5-ethyl 2-methyl hexane. So we'll do 1, 2, 3, 4, 5, 6. And at the 5 positions, so 1, 2, 3, 4, 5, we're going to put an ethyl. And at the 2 position, we're going to put a methyl. All right, when we do this, first, let's check the longest chain. Our longest chain was hexane, but if we look, we've got 1, 2, 3, 4, 5, 6, 7. We can get a longer chain by numbering it that way. So 7 is going to be our longest chain. It will be heptane. Now we need to decide which side to number it from. If we number from this side, it'd be 1, 2. Our first substituent would be at position 2. Here, our first substituent, 1, 2, 3, is at position 3. So that means we need to number from that left side. 1, 2, 3, 4, 5, 6, 7. So it's heptane instead of hexane. And now our substituents are methyls at the 2 and the 5 position. So we're going to call it 2,5 dimethyl heptane. 2,5 dimethyl heptane. All right, so not too bad. Let's look at 2-methyl 2-isopropyl heptane. So 2-methyl 2-isopropyl heptane. So again, let's draw the heptane first. So 1, 2, 3, 4, 5, 6, 7. And we have a methyl and an isopropyl there. So I'm going to put the methyl there and our isopropyl there. And so now when we look at that, let's start with the longest chain. So we had 7, but let's look at it. If we number from here, we've got 1, 2, 3, 4, 5, 6, 7, 8. It would be octane instead of heptane. So we have a longer chain, so we know the heptane isn't correct. Now, as far as numbering it, this one's pretty obvious because if we number from this side, our numbers are going to be big when we get over here. So we're going to number it from this side. So 1, 2, 3, 4, 5, 6, 7, 8. And so that one is octane. Our substituents are going to be at the 2 position, we've got a methyl, and at the 3 position, we've got 2 methyls. Now, when you look at that, that looks kind of weird, but again, it's okay. It's okay to have something that looks a little weird when you draw it. So we've got trimethyl would be 2, 3, 3 trimethyl. So 2, 3, 3 trimethyl, and 8 carbons would be octane. So 2,3,3 trimethyl octane. All right, and now let's look at this one. We've got 5,5,6 trimethyl octane. So 5,5,6 trimethyl octane. Okay, so We'll do 1, 2, 3, 4, 5, 6, 7, 8. And then at the 5 position, 1, 2, 3, 4, 5, we've got 2 methyls there. And at the 6th position, we've got another methyl. When we look at this, there's no way to draw this that will give us a longer chain. So octane is correct. It doesn't matter there. The numbering and the side that we number from is incorrect. Because if we number from this side, we get 5, 5, 6. If we number from this side, 1, 2, 3, we get 3, 4, 4. So we'll number from this side. 1, 2, 3, 4, 5, 6, 7, 8. And that should take care of it. So 3, 4, 4. So we'll 3, 4, 4, methyl octane. All right, so I like that kind of problem. I think that's kind of a fun kind of problem there. All right, let's go back to our presentation and let's look at cycloalkanes. So when we're doing cycloalkanes using the IUPAC nomenclature, the cycloalkanes are named using the similar rules, but the prefix cyclo immediately precedes the name of the parent. So that's really the biggest difference. Now, there's a couple of other subtleties that we'll look at here in just a moment. So step 1, find the parent cycloalkane. All right, so like for example, on this one, clearly we have a 6-membered ring, so we call that cyclohexane. All right, so step 1 is always going to figure out what your parent cycloalkane is going to be. When it comes to numbering the substituents in cycloalkanes, there's a couple of little subtleties that are different. All right, so if you only have one substituent, then there's no need to put a number there because it's implied to be 1, and we don't need to put that number in that case. So we wouldn't call this like 1-methyl cyclohexane. We would just call it methyl cyclohexane. And instead of calling this 1-tert-butyl cyclopentane, we just call it tert-butyl cyclopentane. So wherever the substituent is, that's going to be assumed to be carbon 1. And if there's only one substituent, then you don't need a number. If you have more than one substituent, you want to begin numbering at one substituent and proceed in the direction around the ring that will give you the lowest possible number for the second substituent. So here we've got 2 methyls, and if we do this one clockwise, so 1, 2, 3, it would give this the number 3. If we went counterclockwise, it would give it the number 5. So the number 3, doing it clockwise, is going to be our better answer in this case. All right. So this would be called 1,3 dimethyl cyclohexane. All right, naming different cycloalkane substituents. So if you've got 2 different substituents, number the ring and assign the lower number to the substituents alphabetically. So we'll put them in alphabetical order. All right, so here we've got ethyl and methyl. If we did 1 for ethyl and 3 for methyl, that would give our earlier letter the lower number. If we did 1 for methyl and 3 for ethyl, that would be the wrong way. And so this is going to be correct to give the lower number to the first one alphabetically. So this would be 1-ethyl 3-methyl cyclohexane. All right. Sometimes this happens on occasion. Alkane versus a cycloalkane. So if the number of carbons in the ring is greater than or equal to the number of carbons in the longest chain, the compound is named as a cycloalkane. So if there are more carbons in the chain, the alkane, then name it as an alkane. And here are some examples of this. Here we've got 6 members in the 6 carbons in the ring. 4 carbons in the chain, so this would be butyl cyclohexane. And in this case, we've got 6 carbons in the chain and 4 carbons in the ring, so we're going to name this as a cyclobutyl group that's attached to this hexane. Because hexane has different positions, we need to indicate where, so we're going to call it 1-cyclobutyl hexane. All right, here are a few examples. This one is ethyl cyclobutane, and again, we don't need a number because there's only the one substituent. On this one, we've got 2 substituents. We've got a methyl and a sec-butyl. The sec-butyl is going to come first, so it will be first alphabetically, and it will give the first number as well. So it'll be 1-sec-butyl, 3-methyl cyclohexane. Okay, and then this one, there's 2 methyl groups. We want to number it so that our second group gets the lowest possible number. So this is 1,2-dimethyl cyclohexane instead of 1,6. We don't want to confuse that. And then here we want to give our second substituent the lowest possible number. So we could do 1, 2, 3, 4, and it would be 1, 2, 4, not 1, 3, 4 or 1, 3, 5. That would be weird. Yeah, 1, 3, 5 would be really weird. So, all right, here we've got a 6-membered ring as our cyclohexane, and we've got a 6 carbon chain. Remember, the rule is if it's greater than or equal to, then the cyclo gets preference. So we're going to call this hexyl cyclohexane. All right, let's look at 44 and 45. And after we're done with those, that will wrap up our first video for this chapter. So let's switch over here. All right, draw the structure to each IUPAC name. So sec-butyl cyclopentane. Almost always best here to draw your parent chain. So cyclopentane, and then a sec-butyl is going to be a butyl where it's grabbed by the second carbon. So we'll do 1. So that would be a sec-butyl group. So that is sec-butyl cyclopentane. All right, cyclobutyl cycloheptane. All right, so cycloheptane, when drawing cycloheptane rings, it's a little bit weird because you're not used to drawing 7-membered rings. And so it can be a little strange. Usually the way I do this is I will draw the first half kind of like I'm drawing a 6-membered ring. And then I will kind of fill it in and give 4 little segments there. It looks a little weird, but that is it. So we've got 7 there. So 1, 2, 3, 4, 5, 6, 7. You know, just do the best you can and make it clear. And if you have to, you can, you know, draw your line segments in darker or whatever to make it clear where your carbons are. All right, I think I've made that worse in any case. So let me try it again here. So like I draw it like I'm going to draw a cyclohexane, and then I do 1, 2, 3, 4. Okay, well, again, that was not beautiful, but it's better than this one. So, and then we've got a cyclobutyl. Cyclobutyl is just a square. All right, looks like I drew a triangle. Again, this is not a artist competition. It is merely a way of designating this. All right, 3-ethyl 1,1-dimethyl cyclohexane. All right, cyclohexane, you're going to get good. Get some scratch paper and draw a bunch of hexagons, and you will just get good at it. So let's do this. All right, and then at the 1 position, it doesn't matter where you put the 1 position. I'm just going to arbitrarily put it there. There are 2 methyls, and then at the 3, 1, 2, 3, we have an ethyl. And so that would be a correct way of drawing that. All right, cyclooctane. Cyclooctane is actually a little bit easier to draw than the cycloheptane, and that's because you're just drawing a stop sign. Again, it's not a competition or anything. Let's see, and arbitrarily pick a position that's 1, so we'll call that one 1, and we've got a diethyl, so 1, 2, 3, 4. All right, so there's the 2 ethyls, and then 1, 2, 3, and at the 4 position, we've got a butyl. So 1, 2, 3, 4. That's a butyl. Okay, so now we've got the same thing we had up here a little bit ago where we've got the wrong name, and we want to figure out what's wrong about it and then fix it. So here we've got 1,5-dimethyl cyclohexane. So let's draw the structure and then come up with the correct name. So let's say this is 1. So there's a methyl. And then 2, 3, 4, 5, there's another methyl. Well, this one's pretty easy. We want to give our second substituent the lowest possible number. So we're going to do 1, 2, 3, 4, 5, 6. So it's going to be 1,3-dimethyl cyclohexane instead. Here, I like to do these in red. 1, 3. Dimethyl cyclohexane. All right, here we've got 1-ethyl-2,6-dimethyl cyclohexane. So again, let's draw a cyclohexane structure. And we'll just arbitrarily, we'll call this 1-ethyl. And then at the 2 position, we'll put a methyl. So 2, 3, 4, 5, 6. We'll put another methyl. Okay. Well, this we've numbered it in. This has been numbered in a way that doesn't give our third substituent the lowest possible number. So I gave our first 2 low possible numbers, but we want to give it so that our third. So we're just going to do 1, 2, 3, 4, 5, 6. So our substituents are at positions 1, 2, and 3. All right. So we're still going to call this an ethyl, but it's going to be at the 2 position. So ethyl's going to come first. So 2-ethyl, 1, 3 dimethyl cyclohexane. All right, 2-methyl cyclopentane. So 2-methyl cyclopentane. All right, so let's draw a cyclopentane, and then we'll just put this there, and that's methyl. All right, so this one is pretty straightforward. If there's only one substituent, then that one substituent doesn't need a number. So the correct name for this is simply going to be methyl cyclopentane. So methyl cyclopentane. All right, here we've got hexyl cyclopentane. You may be able to tell already what the issue is. All right, and I'll just arbitrarily say it is there. So 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay, so here our issue is that we've got 6 carbons in this chain, and we've got 5 carbons in the ring, and since there's 6 carbons in that chain, we need to name it after this. So it's going to be hexane, and our cyclopentyl group is going to be at carbon 1. So 1, 2, 3, 4, 5, 6. So we're going to call this 1 cyclopentyl hexane. And that is the name of that structure. All right, well, that is the end of video 1. And in our next, I think that's the end of video 1. Yes, in our next one, we're going to look at common names.